Welcome, everyone. Thank you for joining us for this edition of the GCAN webinar series. Today's webinar is presented by GCAN, the Gulf of Mexico Coastal Acidification Network, by GCOOS, the Gulf of Mexico Coastal Ocean Observing System, and by NOAA OAP, the National Oceanic and Atmospheric Administration Ocean Acidification Program. My name is Michael Aquafreda, and I work with the NOAA Ocean Acidification Program. I'll be moderating today's session. The goal of the GCAN webinar series is to provide relevant information about ocean and coastal acidification that's occurring in the Gulf of Mexico. Our vision is a Gulf of Mexico that is resilient and prepared to address and adapt to coastal and ocean acidification. During the presentation, all participants are in listen-only mode. You are welcome to type any questions into the questions box, which can be found at the bottom of the control panel on the right-hand side of your screen. We'll be monitoring incoming questions and we'll pose them to our speaker during the question and answer section, which will begin immediately after the presentation. The webinar is being recorded and will be available on the GCAN webpage sometime over the next couple weeks. Additionally, we welcome your input on who you would like to hear from in future GCAN webinars, as well as what topics or resources you would like GCAN webinars to cover. If you have any ideas, please type those into the question box, and we will take them into consideration as we plan for future webinars. The title of today's presentation is Coastal Acidification Monitoring and State-Level Actions. I'm very pleased to introduce today's speaker, Melissa Rae McCutcheon. Melissa is a Ph.D. candidate in Coastal and Marine Systems Science at the Harte Research Institute for Gulf of Mexico Studies at Texas A&M University-Corpus Christi. Melissa works as a research assistant in the Ecosystem Science and Modeling Group led by Xin-Ping Hu. Her dissertation work has examined spatial and temporal variability in the carbonate system of the Texas estuaries, with a focus on the physical, biological, and geochemical controls on the estuarine carbonate system. Beyond research, Melissa has dedicated a lot of time to science communication, science education, science communication, and understanding the application of science in policy and management decisions. She plans to pursue a career in one of these sectors after graduating next year. At this time, I'd like to pass it over to Melissa. Melissa, I am now making you the presenter.
Okay. Does that look right for you?
Yes, we see your presentation. You could take it away.
Okay, great. Thank you. So thank you so much for inviting me to be here today. I was really honored to be asked to do this. And I'm going to be talking about a couple of different kind of loosely related topics that I thought would be of interest to the GCAN community. So first, I will talk about an estuarine acidification project. That's something that I've worked on for my dissertation. And I'll specifically be focusing on comparing two different types of monitoring. And then next, I will talk about the actions and investments that states have made regarding ocean acidification. And just a few acknowledgments that I'd like to make before continuing. Several folks from Texas A&M University-Corpus Christi that I've worked with throughout the years who have helped in providing some of this data that I'll be sharing with you today. Xin-Ping Hu specifically, who is my academic advisor, a couple different people from Ocean Conservancy, both Sarah Cooley and Ryan Ono helped me a lot last year while I was interning at Ocean Conservancy. That was an NSF-funded non-academic research internship for graduate student position. So thank you to them. And then some of this work was also funded by the United States EPA, specifically through the Coastal Bend Bays and Estuaries program. So thank you to that as well. And so I'm going to be talking first, generally, an introduction about ocean acidification and coastal and estuarine carbonate chemistry. And then within that introduction, I'll also give a little bit more detail about background on the Texas estuaries from work that has come out of our lab. And that will help to better lead us into the second point, which will be to discuss that comparison of two different types of monitoring, which occurred at the Mission-Aransas Ship Channel on the Texas coast. And then I will talk about what states are doing to address this issue. So that will be a little bit of a transition. And finally, I'll wrap it up with some final thoughts. So moving into the introduction, I believe probably everybody listening in is pretty familiar with the general causes of ocean acidification, but here's just a short review. OA is a global change and a global threat to ecosystems and communities. And on a global scale, acidification is occurring because atmospheric carbon dioxide is absorbed into ocean surface waters. So we can see on this figure, the red line is that increasing atmospheric carbon dioxide. And then with that, you can see that maybe orange line is the coinciding increase in PCO2 or partial pressure of CO2 in ocean waters. And so, you know, these atmospheric levels of CO2 have been on the rise since the Industrial Revolution. And in the process of the ocean absorbing that CO2, which, you know, may mitigate some climate change issues, it essentially, that CO2 is a weak acid in the seawater, so it's going to be lowering that seawater pH. And at the same time, carbonate ion concentration in the seawater is also lowered as the carbonate ions buffer the acid addition. So all of this carbonate chemistry is controlled by the changing speciation of inorganic carbon, or CO2, in seawater, basically. And then there's just a couple of different parameters that I wanted to mention to make sure that if they come up in the talk, everybody's familiar with what I'm talking about. So I'm sure everybody's familiar with pH. PCO2, again, is the partial pressure of carbon dioxide in the water. Total alkalinity, that is the acid neutralizing capacity of the water, and it usually in seawater mainly consists of carbonate and bicarbonate ions. And then the final thing, I'll just be calling it omega. It's the saturation state of calcium carbonate. So it's just basically the product of calcium and carbonate versus how much could be dissolved in water at the given temperature and salinity for saturation. And so, you know, while that cause for ocean acidification on a global scale is really well understood, the coastal oceans and estuaries are a much more complex environment, and there are an array of biogeochemical processes that can locally enhance or alleviate acidification in estuaries. So here's a list of some of those things. You know, our lab has worked to consider several of these causes to coastal acidification in our region. But, you know, you have really substantial biogeochemical processes occurring in the coastal ocean and estuaries. It's where the land meets the sea, and so you have that river water coming in that might be carrying nutrients and organic matter. Also just variations in the amount of that freshwater inflow and the river chemistry itself can be important in certain regions. Physical mixing processes can be important in a lot of regions. That could include tides, or it could include coastal upwelling, which is, you know, something really significant to like the United States West Coast. And then in shallow water, you know, submarine groundwater discharge can also play a role. And the last thing to note is just, you know, pollution from vessels. You have ocean going vessels more densely located in these coastal regions, and so that nitric and sulfuric oxide can dissolve into the ocean waters. And so of all of those processes that may add to coastal acidification, eutrophication, or the excess nutrient loading, is likely the most substantial contributor to coastal acidification on a global scale. So eutrophication often results in enhanced primary production in surface waters, and then subsequent respiration of organic matter in the bottom waters. That respiration uses oxygen, so it would reduce the concentration of oxygen in the water, but it also produces carbon dioxide, adding that weak acid to the water. So this is why we see the co-occurrence of hypoxia and acidification, because they're both associated to that aerobic respiration. And this figure is depicting evidence of coastal acidification that's associated with hypoxia in the well-known Gulf of Mexico dead zone. So this is, you know, one of the leading examples, something that has been studied quite a lot. But, you know, estuaries can also be experiencing this. And so this map is basically showing how expansive the problem of eutrophication-driven hypoxia is. So there are 480 red dots represented here on the map, each of which is documenting a case of hypoxia related to human activities. And so, it is likely that eutrophication-driven acidification is just as widespread as that hypoxia. And I like using this figure to illustrate the relationship between eutrophication-induced hypoxia and acidification. You can see the strong association between dissolved oxygen levels and pH, as it has occurred in several different systems. So you can see two different estuarine environments. Corpus Christi Bay, which is a bay that we work in here in Texas, is shown in blue. In black, you can see another estuarine environment, Long Island Sound, and then the red data are from the northern Gulf of Mexico. And the red line is showing the cutoff of what's typically classified as hypoxic water. So all of these systems reached hypoxic conditions. But what you can see differs between these systems is the level of pH change that was observed as associated with a given reduction in dissolved oxygen. For example, based on the equations generated by linear regression of these data, decreases in DO of 200 micromoles per kilogram would lead to a pH decrease of 0.14 in Corpus Christi Bay, whereas that same decrease in DO would lead to a pH decline of 0.42 in the northern Gulf of Mexico and 0.56 in Long Island Sound. So this is all to say that while this association between hypoxia and acidification is widespread, not all coastal and estuarine waters are created equal as to how their carbonate system will respond to different stressors, such as elevated aerobic respiration. And the extent of that estuarine and coastal acidification differs based on the intrinsic buffer capacity of the water bodies in question. So the Texas estuaries that our lab primarily works in are relatively high buffer capacity and therefore experience less of a change. And just to kind of show that here, the reason for that elevated buffer capacity in Texas are listed here. And some of these can be exhibited in other estuaries globally as well. But, we experience relatively high riverine alkalinity, so high acid neutralizing capacity. In that top right figure, that funnel-shaped TA distribution reflects the vastly different freshwater end member compositions in this narrow latitudinal area. But we can see that the low salinity waters, which you'd find in the upper estuary, often have alkalinity that's much higher even than offshore waters. And then other things contributing to that elevated buffer capacity are high productivity in the region and high levels of evaporation, which can concentrate those carbonate ion concentration. And so despite that relatively high buffer capacity that we know these Texas estuaries to have, the Texas estuaries are still facing their own problem with long-term acidification. So a lot of the work that has been done in the Texas estuaries coming out of our lab was motivated by this finding of long-term acidification and long-term decreases in alkalinity in the Texas estuaries. So this figure was using more than 40 years of data from the Texas Commission on Environmental Quality, and we were able to detect acidification in the majority of the Texas estuaries. So anything that you can see in green on this figure experienced long-term alkalinity decline. And this long-term alkalinity decrease has been attributed to reduced freshwater inflow because of human diversion and water use. So diverting that high alkalinity river water that would otherwise contribute substantially to the estuary's alkalinity budget. And then also as for pH, using that long-term data set, it was also found to be declining in the majority of estuaries. And some of the pH decline rates in certain estuaries far exceeded that of the open ocean acidification rate. And I'm sure a lot of you are, well versed about why it's important to study the coastal and estuarine carbonate chemistry. But, just highlighting these couple of points, acidification can negatively affect the ability of calcifying organisms to build and maintain their skeletons. And that's important because calcareous organisms are often really economically important, like the Dungeness crabs that are harvested on the West Coast, or the coral reefs that are really supportive of tourism, where they can be really ecologically important, like pteropods that are the base of food chains in some regions, and coral and oyster reefs, which are habitats and basically ecosystem engineers that support marine diversity. And, you know, along with the calcareous organisms, it can also impact other biological processes. So growth, survival, fertilization, behavior, all of these things have also been found to be altered in some organisms. And then, you know, specifically for Texas, why is this important? So, you know, I do most of my work in Texas. The Gulf of Mexico harvests a lot of oysters. I'm sure you're all familiar with that. And Texas is the second leading state in oyster harvests. And so 2014 to 2016 data showed that $14.5 million in landings revenue comes from oysters for the state of Texas. And also really importantly is that oyster aquaculture industry is just beginning here in Texas. So it was just in 2019 that a law was passed allowing oyster aquaculture here for the first time. Whereas, you know, it was never not allowed in other states, but it's something that's new here in Texas, and it could be a really substantial industry. And then in addition, I just wanted to highlight, you know, outside of the biological aspect, it's important for the public and a lot of different stakeholders. I think that there's one other good reason that coastal carbonate chemistry is important to the scientific community, and that's the global carbon budget contribution. So, you know, there's really large uncertainties in the role of estuaries in the global carbon budget, but it is believed that the coastal ocean and estuaries have disproportionately large contribution to the carbon budget based on their size relative to the open ocean, as you can see in this figure. And so, you know, it's going to be important and necessary that we better constrain the global carbon budget to keep improving climate change projections. So another good reason to have concern. So I'll move into that case study. This was monitoring that we conducted at the Mission-Aransas Ship Channel. So this is the ship channel that connects the Mission-Aransas estuary on the Texas coast to the Gulf of Mexico. And again, there are two types of monitoring that we conducted here that I'll be comparing. So the first was that we deployed sensors. Those sensors were deployed for a period of 10 months, and they were taking hourly measurements. So we had a SAMI CO2 instrument measuring PCO2, and we had a CFET instrument measuring pH. You know, and I would have loved to have left these deployed for longer, but the research pier where they were deployed was unfortunately taken out in the aftermath of Hurricane Harvey. So we settle at this point for these 10 months of data. But this is what that monitoring data looked like over that 10-month period. And then the other type of sample collection that we used was just the discrete bottle sample collection, where we would bring it back to the laboratory for analysis. This was done for more than 5 years, and we would measure the dissolved inorganic carbon, pH, and total alkalinity. And then we would be able to calculate PCO2 so that we would again have pH and PCO2 that could be compared to that sensor data. And just to note, this is just one of multiple locations in the Mission-Aransas estuary where our lab has been sampling. So although I won't focus on any data from the other stations today, I just wanted to highlight, you know, this method generally allows for better spatial coverage, which can be important in estuarine systems where there's substantial spatial heterogeneity. So the first thing that I want to talk about is, you know, while neither of our 10 months of sensor data or our 5 years of discrete bottle sample data are long enough to look for any real long-term trends in the carbonate system to determine if this area is acidifying, they're definitely useful for looking at shorter-term variability, such as seasonal patterns. And so seasonal patterns are really common in coastal and estuarine systems. because of, changes in freshwater inflow and changes in net community metabolism associated with temperature. And so at this location, the high PCO2 and low pH were observed in the summertime. And that is likely because of elevated respiration during the summertime, which is stimulated by the much warmer temperatures. We can even see that, when we deploy anything, we can see the difference in biofouling on the equipment during the winter and summer. And so, that sensor data was adequately able to pick up differences in the seasons. As well as that, our long-term or 5-year discrete sample collection was also able to detect significant differences in both pH and PCO2 between different seasons. So using that continuous sampling, what we found was that for both pH and PCO2, all seasons were significantly different from one another, while spring and fall were not significantly different for the discrete sampling. So this could be simply because the 1-year sampling period for the discrete monitoring or for the continuous monitoring was not representative of the fall and spring variability that we could detect over the multiple years, or it could be just a result of it being easier to detect a significant difference when there are so many data points like you get when you do those hourly measurements. And then next, I want to talk about diel variability. So this is an obvious advantage of using sensors for monitoring a system, is that you can observe this short-term temporal variability that you cannot capture by taking bottle samples and bringing them back to lab. And so this figure is showing a single representative day from each season so that you can see how the profile would look for both pH and PCO2 as it fluctuates over a day's time. And so representative days were chosen as days that had diel range equal to the average diel range for that season. And so that, can be important because these diel fluctuations might exceed biological thresholds, and it would also be important for your flux calculations. But basically, specific to this location, what we find is that diel variability is not very substantial compared to many other coastal locations. So the average daily range, which would be the daily maximum minus the daily minimum for pH, was 0.09, and for PCO2 was 60. So, that is, fairly substantial variability if you think about it compared to the magnitude of long-term trends in the open ocean. But those daily ranges were much less than a lot of other estuaries that currently also have these sensors deployed. So the EPA's National Estuary Program has these sensors deployed in multiple estuaries. And in those estuaries, there's often much more variability. That might be due to this sensor's location being closer to the open ocean rather than being more so in the upper estuary. Next, I just want to talk through how the different sampling methods compare. So these box plots are showing seasonal variability in pH and PCO2 between the sampling methods. So the light gray boxes are the discrete monitoring. So that's spanning more than 5 years of monitoring. The dark gray is the discrete data during only the period of time when the sensors were deployed, and the black is the data from the sensors. And so you can use this to look for differences between the sampling types. So I used two-way ANOVAs with sampling type and season as the two factors. And since there was a significant interaction between sampling type and season, we know that the differences between sampling types were not the same across all seasons. So a one-way ANOVA was conducted to examine the difference between sampling types within each season. So what I'll be presenting to you is the results of those multiple comparisons between sampling types that we did to look for differences between sampling types. So basically what I want you to look for is any difference in the lightest gray or the discrete data within a season would just indicate that the period of the sensor deployment just wasn't representative of that season over the longer 5-year span of time. But what's really important is the differences between the darker gray, which is the discrete data during the sensor deployment, and the black, which is the sensor data, would indicate that the sensor monitoring and discrete sample monitoring were not in agreement for what the average in this system was over time. And so we can see there was no significant difference in pH measured between the different sampling types for either winter or spring. But for summer, there was a difference between the multiple comparisons, including that we saw that the sensor data was different from the discrete during the sensor period, meaning that that discrete sample collection was not accurately capturing the mean that was able to be captured by the sensors. And I think that's really because, you know, the greatest mean difference between daytime and nighttime pH, which is what I'm showing on the bottom figure, was observed in the summer. So pH was on average 0.03 higher at night than during the day in the summer months. And so this is likely why the discrete sampling during only the daytime in the summer could not accurately represent the mean of the summertime sensor pH data. And now I will go into showing you the same thing for PCO2. So in winter, again, is when we were able to see that there was a difference between the sensor and the discrete data taken during the sensor period. And as we can see, as far as differences between daytime and nighttime PCO2, winter did show one of the greatest differences between daytime and nighttime PCO2, which could explain this divergence between the methods. Also, it's interesting to point out that that day-night difference is not the same all year long. And in fact, during the winter time, we found the opposite day-night difference from what would be expected from biological activity, where photosynthesis is taking place only during the day. But overall, looking at both, you know, the pH and PCO2, we see that there was alignment between averages from the sensor and discrete data during the sensor period for the rest of these seasons. And so basically, the discrete sampling method is performing pretty well. It's able to capture the same mean in the system from a statistical standpoint for either pH or PCO2 during the majority of seasons, but there are a couple cases in which, you know, go to show that it's definitely not perfect. Just another example showing that the system can probably be well characterized by either method. So here on this figure, you can see the sensor data in gray, the discrete sample data in black. And, you know, using ANCOVA, you can see there's no interaction. So these relationships are not different. So we're able to find the same relationships. They're both generally maintained between carbonate system parameters with temperature and salinity, no matter the type of sampling that's taking place. I will say, however, that using other environmental sensor data from the area to look at relationships between variables to try to help us understand what's driving the system, we found that the sensor data proved to be a little more useful in determining those relationships with other environmental parameters. But that's likely because of the monitoring framework for those variables, as well as the sheer amount of data points available when using sensor data. And then the last thing that I want to talk about for this section of the talk is how you can compare the other variables that are calculated within the carbonate system between these two different sampling types. So, you know, it's really cool when working with the carbonate system that you can calculate all the other parameters from having just any two. And that's especially useful since the parameter that has been deemed to be potentially the most biologically relevant is not what is directly measured. And so, however, what you find is there's a certain amount of error associated with those calculations. So the errors that I'm presenting in this box were either specified by the instrument and the methodology, or in the case of calculated variables, such as PCO2 for the discrete samples and omega for both, they were calculated using error propagation function in the C-carb package in R. What you can see is that the error associated with omega is much higher for the sensor data than it is for the discrete samples. This is likely because of the uncertainty of pH from the sensors that is much greater than what we achieve for analytical precision in the laboratory. It may also be because the coupling of PCO2 and pH is not mathematically favorable when doing the speciation calculations. But maybe this will be improved over time as we get pH sensors that perform with better precision and accuracy, or as sensors are developed that can measure variables that can better couple for calculations, such as dissolved inorganic carbon. And just to display, what that omega would look like for the discrete samples versus the sensor data, you can see our discrete samples at this location, omega was almost never below 1.5, but calculations from the sensors actually occasionally reported under saturation. And in all of the Texas systems, we've really only ever seen under saturation anywhere in this region, mostly during flooding in the more upper portions of the estuary. So I definitely, question these calculations. I think there's room for improvement. I think this is something worth investigating and developing further better sensors so that we can more accurately calculate these biologically relevant parameters. And with that, I'll finish that discussion of the comparison between the sensors and discrete sampling. And now I want to talk about states taking action. And so looking at policy and investment on OA that states have made. So again, this is something that I worked on with Ocean Conservancy. And so this map is adapted from an infographic created by Ocean Conservancy while I was working there with them last year. Given that acidification has already impacted the economies of coastal states, and people in the industry have been concerned about this for a while now, states have started to care about ocean acidification and take action to better understand them and this problem in their state. So looking at this map, it's showing all actions related to ocean acidification that have been taken at the state level, as well as some other pieces of information that may provide insight for future opportunities for states to begin or advance their action on OA. So all data presented here, I just wanted to note, are up to date as of the end of last year. So any actions taken by states this year would not be included in this discussion. But I'm going to go ahead and walk you through this visual and talk about the three main types of state actions that I really saw in this analysis. So those three things are legislation, state councils, and appropriations. And so first, talking about legislation regarding OA. So on this map, all the states that are in blue have at least introduced bills mentioning ocean acidification. Those that are in light blue have had legislation introduced but not passed, and those that are in dark blue have passed that legislation. So I want to highlight that it just takes mentioning OA for a state to be blue on this map, but some mentions might be less meaningful, like maybe just listing OA amongst a list of other environmental concerns. So I'll talk about that a little more as we go through. But as I go through the actual numbers of pieces of legislation, like what you see here, I also decided to put another number in parentheses. That is the number of those bills that mention OA in what I consider a pretty substantive way. So this may be a little subjective, but I decided it was substantive if the legislation created a state council surrounding OA, dedicated funds to OA, or focused on, rather than just mentioning, an array of ocean-specific issues that needed addressed, which included OA. So here I put, the bill totals up for the West Coast first, because they are the largest amongst any of the state for pieces of past legislation. Of these, California took the first state action on OA in 2008 by passing legislation that listed ocean acidification amongst the items that the Ocean Protection Council could fund. And so since then, these states have been pretty active at trying to at least get mentions of OA in multiple bills. After the West Coast states, the state with the next greatest number of passed legislation mentioning OA is Maine, with 3 bills that mention OA, 2 of which I consider to be substantive mentions. And the states with the next greatest number of passed legislation with mentions of OA are Alaska, Hawaii, New Hampshire, and New Jersey. And I just wanted to highlight that of those, I didn't determine either of New Jersey's mentions to really be substantive. One was aimed at keeping open a NOAA lab that studied OA. The other was really aimed at rejecting seismic blasting plans in Barnegat Bay. So, their legislation has really done a little less to address OA. And then finally, here are all the states that have passed just one piece of legislation mentioning OA. Of those, most of them were substantive because most of them made a council. That was not the case in North Carolina, though. The aim of that bill was actually to consider physical ocean processes for alternative energy. So altogether here, what we see is that 13 states have passed legislation mentioning ocean acidification. 4 other states have introduced but not passed bills with mentions of OA. So, I think this is really a lot. It's more than I expected to see. And so now that you have this picture of legislation passed, I want to be clear that in many states, there was a lot more that was introduced than was even passed. So for example, Washington State, who's been kind of the most proactive on the ocean acidification front, has actually introduced 20 bills that mention OA. We can see that of that 20, only 8 have passed. But, so states are trying to do a lot to push this message. And the next thing I want to talk through is state councils. So several states have developed councils to focus on OA. These might be called councils, panels, commissions, task force, whatever it may be. On this map, you can see this as the diagonal lines on the states, and that represents that the state legislatively created this type of a group. And the stated authority of these councils is basically to bring together scientists and stakeholders and decision makers on this topic to identify the threat that is posed by OA to the state, identify any data gaps, and make recommendations for state actions. And I'm going to just kind of go through when these were created. So the first state to create this type of a council was Washington State, and that was where the governor convened a blue ribbon panel on ocean acidification that happened in 2011. Since then, the West Coast followed shortly thereafter. In 2013, Oregon and California got their own councils. In 2014, we can see that Maine and Maryland jumped on board to get their own councils to, have a dedicated group to look at ocean acidification and what can be done. Then New York, New Hampshire, and Rhode Island jumped on board. And finally, Massachusetts was the most recent in 2018 to legislatively create some type of council. So altogether, 9 states have legislatively created a council that is specifically meant to focus on ocean acidification. And there's actually a couple of other councils or reports that have been put out from like a state agency or something like that that were not legislatively created. So just to mention, both New Jersey and Delaware in 2015 had some type of an assemblage within their Department of Environmental Protection. So they have been, working on this as well. And then I just wanted to highlight, when these councils are have been completed. So, some of these were just a one-year thing where they wrote up a report about the state of OA in that state's waters, whereas others are a little more extensive in that they are ongoing indefinitely. So any of the things that you see in the blue here, they're ongoing indefinitely. That includes Oregon, Washington, New Hampshire, and Maine. California also still has their ongoing ocean acidification and the Hypoxia Science Task Force. At this point, it looks like they're meant to continue to be convened through March 2021, but there's potential for extension. And then Massachusetts and New York were both meant to have been completed by this point in time. They were each meant to be a one-year council, but they are still currently ongoing since they have not yet released their reports. So next, I just wanted to show you what state funds have been dedicated to OA. So several states have included direct appropriation of funds in their actions taken on OA. The purpose of those funds has primarily been to fund research on OA and to fill in data gaps required to better understand the impacts in the state. So, a good portion of that money in a lot of places is going toward monitoring efforts, which in many cases are probably similar to the types of sampling that I showed you in the first half of this talk. But to a lesser degree, some of that funding is supporting the councils in some locations. But thus far, none of these funds have been going to implementation of any sort of mitigation strategies. And in some cases, you'll find that the appropriations are vague about how they can be used, and others specifically specify what type of OA research is to be conducted, which might also include the context of multiple stressors. So as I show the amount of funds appropriated, you can see the little writing on top is showing how much was toward just OA, or how much was toward what I put as OA plus, which was kind of that multiple stressor context. So, different states have different ways to look at it. But, the first funds that were legislatively appropriate came from Washington State in 2013, following a 2012 executive order from the governor to implement the recommendations from the Blue Ribbon Panel. Washington is the leader in total state funds dedicated to OA. You can see more than $10 million thus far. California follows. The Ocean Protection Council has granted a lot of money for OA research. And then, Oregon and Alaska follow thereafter. Alaska's appropriation was a one-time appropriation for monitoring in the Gulf of Alaska. And so moving on from appropriations, I promise this is the final slide that I'm going to show this map. I just wanted to wrap up this state action discussion by talking about whether the amount of action taken by the states correspond to that state's vulnerability to OA. And while there's a lot of different metrics that you can use to look at vulnerability, we kind of decided to use NOAA's ocean economy data, specifically from the living marine resources or marine tourism and recreation sectors of the economy, which I figured would be threatened by OA if OA were to worsen in a given state. And so the colored outlines around the states are representing the number of individuals employed in those sectors that might be at threat. So states with the red outline have more than 100,000 jobs that might be threatened, and states with the yellow outline have more than 30,000 jobs. And you can see that for the most part, the amount of state action aligns with the number of threatened jobs, with a few notable exceptions. For example, Oregon and New Hampshire both have less than 30,000 employed in sectors threatened by OA, and yet they've taken pretty advanced action on OA. And also, Oregon and New Hampshire have relatively low percent of the population employed and percent of GDP coming from ocean sectors. Those were metrics that I also looked at to, see if that could explain these patterns that we were seeing. But, either way that I looked at it, they are not at as much threat, but they are taking action. Whereas conversely, there are states, most notably here in the Gulf of Mexico, that could be economically vulnerable, but have yet to take action on OA. So it seems that the degree of state level action can serve as a proxy for the state perceived importance on the issue, and a lot of states are concerned. So whether or not the state level is the best level to be trying to address OA, you know, I'm uncertain about that, but what we can see, this sort of nationwide view may help support greater vertical integration, link those state efforts to more regional efforts, and link all of that to federal research funding and policy. So finally, I will wrap it up. First, in the summary and implications, I want to talk about kind of Texas specifically. Where do things stand in Texas? If you remember this map on the right, there is long-term acidification, but I wanted to highlight that despite that long-term acidification, current carbonate chemistry conditions remain very suitable for calcifiers in this region. Also, in looking at that policy analysis, Texas was among several other Gulf states that have yet to take any action on OA. And, you know, obviously acidification is a little less of a present threat in the Gulf compared to higher latitudes or areas with upwelling, but the Gulf would have a lot to lose, as we see by the number of people employed in those ocean sectors. And so Texas, especially now that they're expanding this new industry of oyster aquaculture, might start to show some concern for OA based on concern that might come from those stakeholders. And, you know, one other thing about Texas is I think it's a prime example that regional management is going to be important, because this system is an example of where freshwater inflow exerts more control than nutrient loading in a lot of cases. And so in Texas, they might want to consider careful management of river discharge. And then more broadly, to summarize and talk about implications, you know, I think we really need to be strategic about the way that we set up acidification monitoring. You know, that first half of the talk kind of demonstrates that. There are different methods out there. Different methods may be appropriate depending on the goal of the monitoring. Both of those methods that I looked at can detect seasonal variability and demonstrate relationships between parameters. And at that given location, there are results as far as parameter averages within a season are very comparable, but that might not be the case in other locations. So that's something to consider. Sensors are really great in that they can help understand variability on those shorter time scales. And then also to highlight, obviously we need long-term data sets to be able to detect a signal of actual long-term acidification amongst that short-term variability. And so that's something, you know, that needs to continue to persist, is the same sampling at locations over time. And then the final thing that I wanted to talk about was the need to continue the momentum of all these state actions that I presented to you. And I think with that, we should really, you know, start to move toward mitigation where possible. All those councils put out reports that have recommendations for mitigation strategies. And that's something that, as of this point in time, that's not where the funding is going. It's still going to the research, which is absolutely necessary, but it'll be important to start making those next steps. And with that, you know, there's the potential to leverage total maximum daily loads, part of the Clean Water Act, potentially to reduce coastal acidification, since the strongest driver of coastal acidification globally seems to be eutrophication. And so it will take a lot of research to determine what level of reduction of any nutrient or organic matter loading would cause us to reach our desirable outcome for OA, but I think that's an important next step. And with that, I would be happy to take any questions from the audience.
Hi, Melissa. Thank you so much for that wonderful presentation. if you would like, you could go ahead and turn on your video camera. Oh, there you are. I'll turn on mine as well. And at this time, I would like to invite all of our attendees to please post some questions in the questions box. You can find that on the bottom right-hand side of your control panel. And I guess the first question that I had, Melissa, has to do with some of the policy work that you discussed. The states that actually had legislation that really had some teeth to it, did those laws get put into place from kind of top-down action or bottom-up grassroots efforts by people in the community organizing? Where did the momentum start, and how did it get pushed through? Melissa, we can't hear you anymore. I think you might be on mute.
Sorry about that. I think that might be a little dependent between different states. You know, the very first actions that were seen, those very initial actions in Washington State coming in 2011, you know, there was a lot of community concern that spurred that, but I think that it was really driven by the governor of the state at the time having a lot of concern and, you know, creating executive orders. And so that was kind of like what got the ball rolling. And I think Washington kind of led the way for other states to realize, you know, they had concern about these issues in their places as well. And in those places, you know, no other place was there necessarily an executive order, but I think it's still, in a lot of cases, was coming through the state assemblies. I'm sure there were advocacy groups working to help inform the people working for those state assemblies, though. So that's always definitely an important component.
Absolutely. Another question that I had had to do with some of the states where they mentioned OA in their legislation, but it really was kind of thrown in. Do you see that as maybe like a separate category on your map, and like how should someone interpret that?
Yeah, that's an interesting question. I think to me, it was like, it seemed like some of the states, it was just if they were passing like any type of legislation that had anything to do with like environmental issues or something, somebody tried to throw it in there. And I don't know if that was, you know, just a certain person in the state's assembly that was like, you know, this might be the starting point to bring this to attention, that this, you know, is an important issue. Because yeah, as the couple different examples that I highlighted like show that, you know, those bills coming from a couple of the states really weren't concerning ocean acidification, and they just somebody felt the need to throw in that mention. So, you know, my hope is that in those states, the fact that it's in legislation at all means that there's some level of concern and that they might continue to move forward.
Yeah, hopefully it's at least on their minds now and something that they could point to in future bills. And then another question I had, and I want to invite our attendees to also add questions to the questions box. But one other question I had relates to your science and also the policy side. In the states where you might not be seeing a strong signal of acidification yet, but they have a lot to lose. So maybe some of those Gulf of Mexico states. How would we convince legislators to take up action, even if it's just monitoring and funding research rather than mitigation? And this might go beyond the scope of what you feel comfortable talking about, but it was just something I thought about.
Yeah, I mean, I've thought about it for Texas, because to me, it's like, I do think at this point, like most of the waters on the Texas coast are very suitable, which is great for this incoming oyster aquaculture industry. Like, I think it could be really big here because the water is very suitable. But I think the fact that we were able to demonstrate, despite that water being suitable, that there are long-term trends toward acidification in a lot of the Texas coastal waters. To me, that would be enough to spur concern at least in the stakeholder community, in the community of people occupying this new aquaculture industry, and maybe with enough concern from them, real management decision makers, policy makers would start to consider it a little more in the region, I think.
Cool. I appreciate your take. Okay, so at this time, oh, look, we got one question coming in. Okay, this is from Ryan Ono, and the question asks, can you talk about the feasibility of installing OA monitoring equipment onto existing water quality monitoring infrastructure? I'd imagine there's quite a lot of economics of scale in terms of existing hardware in the water and parameters already being tracked.
Yeah, absolutely. That's something, I know being close to a national estuarine research reserve, they have several platforms set up where they have several different types of environmental monitoring occurring. They have, a team of people that go out there to switch out sensors and download data and do all of that stuff. And so I think, it would absolutely be beneficial to think about that infrastructure that's already there and co-locate any sensors that could be taken out to, be able to look at those correlates between different environmental parameters. I think the difficulty comes in that sensors for measurement of carbonate chemistry, first off, are pretty expensive, I think, relative to a lot of the other sensors that are widely deployed. So, finding the funding for that is one thing. That's like, we got this funding from the EPA to get those two sensors, but that's one location, whereas a lot more funding would be needed to be able to get a lot more substantial deployment of sensors over, a greater amount of space to capture spatial variability. So yeah, at this point, that's a funding issue. That's also here in Texas and probably the majority of the Gulf of Mexico. There's issues with biofouling for those sensors as well. We had a pretty unique setup to kind of combat the issue of biofouling for those sensors that I deployed. So that would also be something that, at least for this region of the world, kind of have to work out the kinks. But I hope that that's something we can move forward in coastal estuarine areas. There's more of that offshore. There's not a lot of that going on yet in the estuaries.
Cool. Well, Melissa, thank you so much for sharing your presentation with us. At this time, I'd like to invite the audience to check out the GCAN webpage where this video will be posted. We have webinars approximately every month, so make sure to check that site for our next installment. And one last time, I'd like to thank our speaker, and everyone have a great day.